Afternoon, everyone. So welcome to the second keynote. So by Dr. Xinwen Fu. And it's my great pleasure to introduce our second keynote speaker, Dr. Xinwen Fu. And Dr. Xinwen Fu will be speaking about a unified view of IoT and the CPS and the trend of research on microcontroller-based IoT. Dr. Xinwen Fu is a professor in the Department of Computer Science, University of Massachusetts Lowell, and he was a tenured associate professor at the University of Central Florida. His current research interests are in computer network security and privacy, and Dr. Fu has published at prestigious conferences, including the 4 top computer security conferences, Oakland CCS, Unix Security, and NDSS, and journals such as ACM IEEE transactions on networking, and IEEE transactions on dependable and secure computing. He spoke at various technical security conferences, including BACnet. His research was reported by various media, including CNN, Wired, and Huffington Post, and Forbes, Yahoo, MIT, Technology Review, PC Magazine, and aired on CNN, domestic and international, and the State Science and Education Channel of China, or CCTV 10. And now I will turn over the floor to Dr. Xinwen Fu.
Thank you, Sheldon, for the introduction. And also I want to thank Rongxing for the invitation. And I caught COVID, it's already 2 weeks. I still have some symptoms, so please bear me if I cough. And so it's my great pleasure to actually share my IoT research. So today we will look at my unified view of IoT and CPS. So here is the outline of this talk. I'm going to first present my view of IoT and CPS. I guess you will have different kind of opinions about IoT and CPS, but let's look at my view of IoT and CPS. So here is a definition of IoT. So IoT basically interconnects everything. So in this video, we can see IoT has a lot of applications. So we may have like a smart agriculture, we may have smart industry, and we may have smart transportation, and we may have smart buildings and many other smart things. So normally, when we talk about smart things, we actually get the data from the field devices and upload the data to the cloud so that we can process the data and make smart decisions based on the data. Okay, so that's about the definition of IoT. So let's look at a few examples of IoT. So here is one typical IoT network in people's mind. So this is a low-cost air quality monitoring network. This is a real network actually called proprietary.com. So this is the architecture of their system. So we have here this proprietary.com device. This is the air quality device which measures PM 2.5. And the device actually supports Wi-Fi. So the data can be actually uploaded to the web server of the company through the Wi-Fi router. And the web server actually provides you a Google map, and you can actually view the data using your computers and using your smartphones and other devices. And if we look at the inside of this sensor, then here are all the components. The key components here are this is actually a microcontroller. It's a very cheap, like a $3 one. And then here, the blue component is the actual air quality sensor. And so the microcontroller here actually reads the sensor data using a UART port. So it's just a bunch of cables. And then this microcontroller, ESP8266 here, actually supports Wi-Fi. So basically, this microcontroller reads data from the sensor and sends the data to the web server. And so this is a typical kind of IoT network. So now let's look at the example of CPS. So CPS, many times in people's mind, is a big system. So we have been working on smart building security. So here is one example here. And so on the right here, then we have this damper. The damper basically has a blade which allows the airflow to flow in. So we can actually control the blade so that the airflow will get in and get out, right? And then how can we control this damper? So we use an actuator. So here, the device here is the actuator, and we actually attach the handle of the damper, which will actually rotate the blade. So we'll attach the handle to this actuator, okay? And then how can we control this actuator? We use a controller. So this is a particular controller which is designed to use together with this actuator, and they are using the twist pair cables to communicate with each other. So the controller will actually send the signals to the actuator, which will rotate here. There's a rotation component here. We'll rotate the handle and open the damper or close the damper. Okay. And of course, normally, you know, in a smart building, then we have the local network so that the controller here can collect to the local network, right? To protect the local network, to protect the building system. Then we have the firewall, and the firewall will actually block the attacks from internet. So let's look at the video here to see actually how the damper works. So you can have some kind of sense of how the damper works. So here you can see this is actually how the damper works. This is a blade, or a plane here, a blade here. And so we can actually rotate this handle to change the angle of the blade so that we can control the airflow. So this is basically how it works. Okay, so now we have looked at the example of IoT. We also looked at the example of CPS. So for my perspective, of course, my perspective is the networking architecture. So the CPS and the IoT are kind of similar. So let's look at this architecture here. So in this architecture, right, and first we have the cyberspace. We have the internet, we have the firewall, then we have the local network. Then people actually can control the devices from the internet or from the local network. Then for a particular IoT and a CPS, what are we doing here? When we talk about things, we often talk about the dumb things like without any kind of communication modules. For example, before we attach this actuator to this damper, of course, you can use hand to change the blade angle, right? But it's not so convenient, but you can do that. So we are talking about those damper things. And then here, of course, we also have this kind of air quality sensor, right? Before we actually use the microcontroller to read the data, it's just a very kind of not so smart thing. So what are we doing here? So what we are doing here, we are doing the same thing for CPS, for IoT. We actually attach either communication modules or actuators to the physical things. So once those things have actually the communication capabilities, they have the cyber kind of capabilities, then we can use controllers, maybe a particular one, to control those devices or collect data from those devices. So you can see here that because of the communication modules that is integrated into the thing, either a CPS big thing or IoT thing here, small thing here. So they have the communication capabilities, so they can actually form very complex networks, right? And for the CPS networks, they often use like their proprietary protocols to communicate between their local networks. So that's one more difference. So you can see here, I see the difference in IoT and the CPS, the difference between IoT and CPS. is the applications. And so for different applications, we use different hardware. Now we may have different OS, we may have different software using different actually programming languages to program the applications, and the networking maybe proprietary and maybe not. Maybe we just use TCP/IP. Maybe we use other like protocols for building automation systems. For example, people have been using the BACnet and KNX. Those are two popular protocols. And the data, of course, are in different formats. But you can see here, from the perspective of a networking architecture, they are same. So what we really did is we just added communication modules to the things so that they can become part of the network, so that we can actually control those things, whatever it's an IoT thing or CPS thing. So from now on, I'm going to use actually the term IoT and not using the CPS term anymore. Okay. And so to show the view actually is kind of valid, so I want to actually present a few attacks from the perspective of the view. So you can see here, we are actually talking about the security and privacy from actually same aspects. So in my view here, and so when we analyze actually the security and the privacy of an IoT or CPS system, we have to look at the whole thing from 5 perspectives, from 5 factors: the hardware, and networking, the OS, software, and the data. So what is hardware? So hardware, for example, right? So the hardware is the actual thing over there. I mean, it's the actual thing having any kind of I/O, and people just attach a cable to the hardware so they can manipulate the hardware. We often heard of the smart car security. In early times, people can just attach cables to the car and change a lot of things, right? And so we have to look at the hardware. So networking, of course, since now those things are smart and have several components, have the communication components, are their protocols secure or not? Do they have authentication? Do they have other kind of encryption and other things in their networking protocols? And the OS is a very interesting topic here. And for many those resource-constrained devices, they don't have like Linux Windows, like a real OS, but they provide like the SDK and the programming libraries. So do those actually OS or the SDK or programming libraries have actually vulnerabilities, right? And so those are about the OS. The software. Software is the third-party application. For example, right? You can use actually the programming development kits to program your own kind of application. And but of course, you are using the existing APIs for that purpose. You can also write your own, right? And so when you actually develop a software, does your software have issues? So the last part is the data. And the data here is when you leave data on your device, are they secure? Particularly, this is important for IoT because often we leave IoT devices in the wild. Okay, so this is my perspective. And so I think we can analyze actually the IoT devices or CPS devices from these 5 perspectives. So I'm going to show you how we do the analysis using these 5 factors. So first, I'm going to show you the IoT attack. So this attack is against the air quality monitoring devices we already saw. And so here is the device, right? As we mentioned before, and this is the inside of this device. And you can see here, we have a micro USB cable here. And originally, this cable, when we bought this device, the cable only supplies power. But when we actually attach a common smartphone micro USB cable, which supports a power supply and communication, and we find that we can actually dump the device firmware out of this microcontroller. And so they don't have any kind of hardware protection. They don't disable actually for example, the UART capability. And you can actually dump the data, and you can actually find the people's Wi-Fi passwords. And if you go to somebody's house, they use this device, you can just attach a micro USB cable and dump all the data out of the device. So you can see the poor design of this device. And they don't have flash actually encryption. And so basically, you can also use this micro USB cable to actually flash a new firmware into the device. Then basically, you can do a lot of things with a new firmware. Okay. And we also did the networking attack against this air quality monitoring device. And so what we did is we first needed to understand the protocol. And to understand the protocol, we construct a test bed. So here is the sensor, right? We want to understand the protocol of this sensor, particularly the communication protocol. So what we did is we use a laptop here, and we set up this laptop as an access point as a Wi-Fi router. Then we install a protocol analysis tool called MITM proxy here. So then now we connect this device to our laptop, and then this MITM proxy will dump all the data. And because this system is not encrypted, right? We can actually check all the traffic details, all the communication details, and between this air quality device and the actual server. And by doing this, we actually find the system architecture of this system, right? And we also find the protocol and also did the format. And we find they actually use a MAC address as the identity of the device. They don't actually really use any kind of authentication in their system. There's not much security. And so, you know, once we understand the protocol, then we can do the air polluting kind of attack. So what we're trying to do here is we can actually create our own software, and our software will behave like their sensor and their device. And we inject like arbitrary data into their system. Their system will take our injected data and compute like an average air pollution and show on the map. So this figure on the top shows the data, the curve before pollution, right? Everything was perfect. And this is actually in Florida. So in Florida, there's no much pollution here. You can see, I mean, all the, you know, PM 2.5 value here is around 0 here. And then we perform the attack. Then you can see now, after we inject arbitrary data, high value data into the server, we can actually pretend to be any sensor of proprietary.com and inject the data into their server. Then now you can see for this particular device, it will show a high value. But in this case, of course, we are using our own device. This is the curve from our own device. So now you can see this map now shows a very large value of PM 2.5, which means severe kind of pollution. Okay, so you can see we can use that 5 factors to analyze this air quality monitoring network, and we just actually need to take care of the particular details. So let's look at another example, the attacks against smart plug. And I guess all of us have smart plugs, maybe not all of them, but I have few at home, and I'm using smart plugs to control my Christmas tree, and so my Christmas tree will actually turn on at 6 p.m. or 5 p.m. and every day, and it will turn off actually maybe at like 11 p.m. And so that's the smart plug. So for this particular device, we are using a popular device from ADMAX. And so this is the ADMAX smart plug. And so this is actually, this device actually is Linux based. And so what it does is you can see here, it has Wi-Fi, right? And the smart plug will connect to the Wi-Fi. And then you can actually control the smart plug remotely and using your smartphone. What happens is that they have actually servers on Amazon EC2. And so basically when you send a command to the device, what happens is your commands will first go to the Amazon EC2. Amazon EC2 will relay your command to this smart plug. You can also control the smart plug at home. And so this is the smart plug. So again, we did a similar kind of a protocol analysis of the whole thing here. And so this is what we found. So we found, so basically, this whole thing has a very poor design. They don't have any kind of a security here. And so for example, they don't use actually crypto to encrypt the communication. They don't use HTTPS or SSL, TLS. And they did use actually something called obfuscation. They did a kind of a bit shifting over sensitive data. But there are many ways to defeat this kind of obfuscation, right? And we can change the input and see how it changes. So then you can see here, the obfuscation will be defeated. So we did reverse engineering the whole communication protocol of the system. So this is what we found. So for this particular smart plug, and we can perform the device scanning attack. So what happens is, for this device, and they use MAC address as username, and they have a default password for each user as 1, 2, 3, 4. So in this way, right, we can program and send authentication information to the server and see how it responds. And this is how it responds. So basically, if the plug is online, if the password is correct, then the server will respond with a code 1070. So you can see for other statuses, right? And it has different response code. So now, based on the response code, then we know the status of the smart plug, right? And so what we did here is because they use the MAC address as the username. MAC address is predictable. Each vendor is allocated with a bunch of, a range of maybe multiple ranges of MAC addresses. And so we can enumerate the MAC address space of this particular vendor, particularly this Wi-Fi adapter. And so we did an enumeration that we can actually find the status of all smart plugs. So one thing here is we found actually many people just use the default password 1, 2, 3, 4. And even they change the password, right? We can still use a brute force attack. But you may ask, okay, what if the user actually use a very strong password? How can you deploy the brute force attack? We can still do that because they don't use any intrusion detection system to report any kind of intrusions. So we don't have the danger of being exposed. But that will take a lot of time, right? And it's still too much time to do that. So luckily, this device has another issue here. So this issue is a very serious issue here. So what we did here is like this. So we actually create a software bot as a fake plug because we want to attack a particular device with a particular MAC address. So our software fake plug will register itself with the company's authentication server. So what happens when we do this, actually the server will kick this real smart plug offline for some time. Then during this time, when our fake plug is online, when the user opens the app and tries to control the original device, actually the user will send her username and password to our fake plug. So in this way, we will get the original smart plug's password. So once we get the password, right, we can use the password to control the original smart plug, right? So you can see, right, this is a network attack. So you just need to understand the particular protocol to deploy this attack. Okay, so we now see, you can see, we can use the 5 factors to analyze the IoT systems, right? So let's look at how we use the 5 perspective or 5 factors to analyze a CPS, in this case, a smart building system. Okay, and this is our test bed, our lab. This is a building automation system installed by Siemens. So they actually installed this building automation system at UCF, and so Siemens did that. And so here, the 2 devices with screens are temperature and humidity sensors. And the 2 devices on the top, the DXR2, right, are actually the controllers. So basically, the controllers will collect the data from these 2 temperature sensors and send it to out. And so for a large system, for a large CPS system, often they have actually a central server. In this case, the central server is called the building management station, and it actually uses Siemens Desigo CC software. And so this software can be used to actually realize all the components in a building automation system. You can see them, okay? And they design the whole thing here. And this is the whole industry, right? Smart building industry here. And you can actually control the device. You can actually control all the building components, okay? And so this is the whole system. So basically here, the controllers collect data from the temperature sensors and forward the data to the Desigo CC, right? And so the current status of a building automation system is the building automation system itself doesn't have much security. So we will look at more things about this. So basically, now we can use Raspberry Pi to perform other attacks, right? And to perform many other things. So we actually purchased a lot of other building automation system components and to show what is danger here. So let's look at the danger here, okay? And so let's first look at the hardware attack against the BS. So we have to understand, the particular physics here. And so for any kind of a system, right, particular system we are not familiar with, we found the difficulty exists in understanding the physical collection here. And but really, the kind of a similar thing to the IoT communication. So in this case, you can see here, and so what we did with the hardware attack is, remember we have the temperature sensors on the panel, and then we try to attack that temperature sensors. So what we did is that we can remove the temperature sensors and hook our Raspberry Pi to the original position of the temperature sensors. We want to actually kind of inject data or commands into the system, right? So what we did is by the physical attack. You can see here, right, in a building, you often see the motion sensors, you often see the temperature sensors installed everywhere around the building. Let me tell you, basically those devices are connected to the building automation system. You can remove them. You can actually hook your own computers like a Raspberry Pi to those positions. But however, one question is, how can you do that? How can you actually hook your computers to a physical system over there? And then you have to understand the communication and the physical cables over there. So basically in this case, and we can just use twist pair cables to collect our Raspberry Pi to the building automation system. But we have to use a particular adapter here. This is called a pair head here. You can see the red and black jacks here, right? And so those are basically the adapter, and so that we can use this Pi and communicate with this adapter. And then here, these twist cables are connected to the system. In this way, we can send commands from the Pi through the adapter to the building automation system. So, of course, you know, we don't find a lot of manuals and literature online. So we have to actually understand the particular building automation protocol ourselves. That's why we actually developed this KNX Bus Dump Tool. So the purpose here is we are using the same head, using the same adapter. We want to actually dump the KNX device raw data. We want to analyze data and see what are the data fields, what are the actual protocol. So we actually did that, and we were able to import the generated hex dump file into Wireshark. So Wireshark has a module which can be used to analyze the KNX data. It's called telegrams, okay? But the Wireshark itself cannot be used to actually dump telegrams because Wireshark is used to work with the TCP/IP network, and this KNX network is a open source protocol for building automation systems. So basically TCP dump, I mean, Wireshark cannot actually dump the telegrams. And so basically, once we have the KNX Bus Dump Tool, and we can actually look at the details of all the telegrams, understand the protocol, and we can do a lot of things. So we planned the tool actually at Black Hat Asia 2022. Okay. So now we understand the building automation system, and we also understand the protocol, data fields. Then we want to show we can do some damage here. So basically, we want to tell the building automation industry, you have to secure your devices. Your devices are exposed to the public within all the buildings. If somebody removes your devices, hook their own Pi or computers to your system, you are doomed. So we actually showed a very kind of not so malicious attack. So we only did a false data injection attack against our panel here. And so we did a man-in-the-middle attack. So the figure here shows the architecture here. So on the left, we have the sensor, the temperature sensor. Then on the right, we have the controller. So our purpose here, we want to actually change the data sent from the sensor to the controller. So we use the two Pis for that purpose. So one client Pi here on the left, communicating with the sensor. And one server Pi here communicating with the device, I mean the controller. The reason we use two Pis because, you know, one Pi can only communicate with, in this case, right, we use one Pi to communicating with one actually Pi hat, the adapter here, right? And so these two Pis are connected to each other using the Ethernet. So because we already understood the protocol and the data fields of the communication between sensor and the controller, we spent a lot of time because, you know, we couldn't find the details of the communication protocol online. So we spent a lot of time to figure out the actual protocol. So once we understand the protocol, we can actually change the temperature, right? So when you change the temperature, then you can see the damper will actually be opened or closed, and to actually change it, to actually stabilize the temperature within a room. So here we show an example using simulation here, and from actually ECE people here. And so we show here, when we actually change the temperature, maybe just 1 degree, okay, the actual energy cost, particularly, you know, in Florida or in Canada, right? Because it's either very cold or very hot. Even you change 1 degree, your AC, your HVAC will work all the time. Then you can imagine the actual energy cost, right? So in this figure here, you can see the blue dashed line here shows the normal kind of energy cost. And then the green line here shows if we change the temperature reading of the sensor to 1 degree, right? We add 1 degree to, and then you can see here. So basically, I mean, as time goes, right, the energy cost is increasing so much. Okay, so if you have any questions, please stop me, and I'm happy to answer your questions. Okay, so we actually did more things on building automation systems. So we just talked about the KNX. KNX is one popular protocol used in Europe. In US, most of the buildings, I mean model buildings, using a lot of protocol called the BACnet. But again, because most of buildings were built some time ago, they don't have any security. So we were thinking, I mean, can we actually enumerate all BACnet devices given the IP? So we can, for example, scan out the IP and see what happens, right? So what we did is we actually designed an automatic tool here. And so for each IP, we use the details of the protocol. We send some packets following the protocol and see how the device will respond. By that way, right, in that way, we know if actually the device is a BACnet device or not. And if it's a BACnet device, we go further, we can actually enumerate the BACnet objects. The BACnet objects here mean the actual devices, actual building components connected to the controller. So once you know those objects, you can send the data, you can send the commands to those objects to change the status of the objects. Okay, so now once you know that, right, once we know all the protocol details, and then we can actually control it. So here, and we actually tried to attack the Siemens control panel. And you can see here, this is the device on the panel, right? And we can send a command from our campus network to actually rotate that actuator. So in this example, and you can see here, so let me show you here. Let's wait, yeah. So in this example, so this is the controller, and this damper is integrated with this controller using something called a TXIO. It's just kind of a digital I/O. Okay, just using a few wires, collecting these two together. That's all. And in this case, you can see we don't actually put a handle. We don't actually connect this actuator to a damper. We just want to show here, you know, if you don't have security for your BS, right? Once people understand the protocols or the physics, they can actually control your device. And if it's a power plant, for example, they may shut down your power plant. That will cause actually tremendous damages to your actually campuses, to your enterprises, right? And so this is what we did, okay? And also, so we found, you know, there's not much research on building automation system yet. I think one reason is most people cannot access the building automation systems. We are lucky to have the panel working with Siemens in this research. So basically, one thing we are doing here is we try to understand if, you know, the software and the hardware of the building automation systems devices are vulnerable to common attacks. For example, the common software attacks, such as buffer overflow and other kind of attacks. So we actually did that, and this is our preliminary results. And so we actually tried a few popular building automation server. This is the open source server, KNX, Canimero, BACnet, and Stack. And we actually found that, you know, by doing fuzzing, we found multiple bugs. Those systems, those software has been over there for a long time, but you can see the software still has a lot of issues. And what is a fuzzing? Fuzzing means we actually send garbage messages into the target and see how the target responds. So normally, if you send garbage messages, if the device or the software crashes, then you know there's a problem. What is the problem? You have to go further and look at the code and see what is the problem. That's why sometimes we need something called a dynamic instrumentation. So we want to find out, you know, what code causes the crash. Okay, great. So now I think we know we can actually use the 5 aspects to talk about the CPS IoT, right? Let's look at some of our work, and also actually we'll also follow other people's work and see some research directions here. So again, here when we actually look at security privacy, we want to look at the security privacy from these 5 perspectives. I call this end-to-end security. You have to actually look at the one end, right, your device, the other end, the server and the user, and you have to secure everything from these 5 aspects. So of course, for security research, we have attack, we have defense. So let's first look at the defense. I'm sorry, attack. So one question we want to ask, what is the root cause of IoT security privacy? So I found many people have been talking about, so the IoT has so many issues. It's because actually we don't have appropriate chips for IoT. All the chips are too expensive. That's a wrong conception. Okay, so we actually did some research. You can see here, companies have been innovating all the chips for IoT. So for example, here for ESP32, it supports Wi-Fi, BLE, Bluetooth, right? Hardware, crypto acceleration, and flash encryption is only around $3. For microchip, at ECC 608 crypto coprocessor, so you can send the data to this coprocessor. It will do the encryption and do other things. It's only about 50 cents. It supports AES, ECC, HMAC, SHA-256, and the random number generator and the secure storage. And so we also test the performance, and they are pretty good actually. You can see here, we did a ECC key generation, and then for ESP32, you can see we can generate the key within 1 second, right? For low-cost application like sensors, we don't need so much real-time kind of properties, right? And so it's okay, right? And also for ECC signature operation, you can see again, it's within 1 second. Maybe you can see here, most of them, it's about 0.1 second. And for the signature verification and generation, okay. And of course, we know, ECC and the public key crypto is used for key exchange. Then after that, we are going to use the symmetric key crypto for data encryption. So what is the performance of data encryption by AES? You can see here, right? For AES key generation, basically a bunch of random numbers. It's in the scale of a microsecond. For AES encryption here, this is the AES encryption here. And so this is the ECC encryption here, right? Again, here you can see most of them are in the scale of microseconds. Okay. And so basically the performance is okay for particular for the sensor application. For those applications do not require real-time kind of properties. So basically, this is our question, right? Are hardware and cost causing the security problems? We say for new devices, it's not actually the hardware and the cost, it's the design, okay? And so we actually tried our own design here, and we designed a air quality system, and we tried to put all our new techniques into the system. We found actually, for a practical secure application, implementing so many security mechanisms is not easy, and it needs a lot of skills. Maybe that's one reason, companies, they don't have the skills. That's why they produce devices with so many problems. Okay. And but we have another twist here. And for large scale applications and like smart buildings and smart grids, there are so many components. When you try to replace one thing, it's very much kind of a labor work. So replacing all the components, all the unsecure components, does actually incur a large cost. So that's why you can see we are still using the unsecure one, but we tried to actually do all kind of mitigation here, right? For example, now people have been trying to understand what vulnerabilities in new IoT application, for example, Bluetooth, right, BLE5. We did some research over there, and people have been trying to understand what is new vulnerability over there, and they try to mitigate the vulnerabilities. And but for smart grids and for smart buildings, we cannot replace all the devices, right? How do we mitigate the risk given the large cost? So sometimes people try to identify the key components which will cause severe damages and try to secure those devices somehow. So those some directions people are doing. And so now let's look at defense. And the defense, we have been actually looking at the secure IoT OS. And many people are doing this. And this is some of our work. And so the key thing here is, we try to fight memory corruption attacks. As we mentioned, many IoT applications are written in C, and C++. And C and C++ is particularly vulnerable to memory corruption attacks like a buffer overflow. Of course, then people have been trying to port Java and Python to program IoT applications, but they are still very rudimentary. So then we were thinking, right, since the IoT applications in C, can we actually apply the traditional address space layout randomization to fight those memory corruption attacks like buffer overflows? So as we know here, in Windows, Linux, Mac, when we actually do the address ASSR, right, and address space randomization. So normally what we do here is we actually load the whole executable to a random address, to a random start address. So basically it means we have to load the whole app into RAM. But in resource-constrained IoT devices, such as those powered by microcontrollers, we don't have so much RAM. We only like a 10K and maybe a few K bytes of RAM. So we cannot do that. And also when we actually implement such kind of applications, right, mechanisms, security mechanisms, we don't want to sacrifice the performance given already limited computing power of those devices. So this is what we did here. So we designed a function-based address space layout randomization scheme for resource-constrained IoT systems. So what we did is, so this is the IoT application. It's already in a flash. We want to actually load the application into the RAM. So what we do here is, so every time, when there's a function to be used, so we have a handler here. So the handler will do this. It will actually load the function into the RAM and put the function randomly within the RAM, right? We only load function needed at this point into the RAM. So the RAM always keeps the current functions that we need to run the application. For those unneeded functions, right, it's still in the flash. So by doing this, right, then you can see we achieve the function-based address space randomization. And but we have to actually address a few challenges because we are moving the functions around within the RAM. So we have to deal with memory management because we're also moving the functions within the function. The code may call another function. So we have to address the memory addressing issues. Okay, but we actually did some work and managed to implement the whole system. And you can see here, this is the performance evaluation of our system. And so here, you can see if our randomization region is like a 5 kilobytes, right? You can see, for the chip we used, it's called a Cyber L11. It only has how many? 6K or 10K of RAM. And so it's really kind of a minimum. But even with that minimum RAM, we can still actually run the application. Okay, we did a test on many applications. It's okay, but we are still improving our system. So now let me summarize today's talk. So in today's talk, we actually discussed the IoT and CPS. I think from the perspective of networking, they are similar. And we also saying, okay, we have to actually secure the IoT from the 5 factors. And we also talking about the recent advance in hardware actually allows secure IoT and CPS. The only problem is for large CPS systems, for large IoT systems, the replacement cost is high. So we have to think about mitigation approaches. That's maybe one direction here. And so for some researcher trends here, because there are so many new applications that we can try to find vulnerabilities in those new applications. And but we are particularly interested in designing secure OS. So for example, can we actually design and implement an OS like Windows, Linux, and Mac OS for IoT? Those systems have a lot of security mechanisms. So I guess that's all for my talk, and thank you very much. So any questions?
Oh, thank you, Dr. Fu, okay, for your interesting talk. Okay, so I will open the floor for questions. So due to the time limitation, maybe we only take maybe 2 questions. How's that? Okay. Yeah. So for audience, you are able to unmute yourself. Okay, speaker to ask Dr. Fu directly, or you can type your question into a chat box. Yeah, please go ahead. Any questions from the audience?
Hi, Professor Fu.
I'm moving. Okay, let me move to here. So yeah, go ahead.
Yeah, I think it's Dr. Rashidi's turn.
Yes.
Yeah, please go ahead. Okay. Yeah.
Thank you, Professor Fu. It was a great presentation. In your presentation, you mentioned that design challenges is one of the reasons that to have insecure IoT system. Can you please provide more information related to that?
So the design challenge here is, for example, for this, let me show you here. For this, so in this device, we use at ECC, the crypto coprocessor, right? And so when this is only 50 cents, but most of the systems, they don't use this kind of chips. So they don't use, they have the capability, they either choose the wrong chips, or even they know the chips, they don't actually implement, for example, TLS and TLS SSL. And so when they design the system, I don't think they have security in mind. So they also do not explore the current advances in the IoT chips. So that's my point over there. So we have to think about it. We have to look at the IoT from these 5 aspects. So when you design your system, you have to look at all these 5 aspects and design your system. That's what we did for our system. We found that, it's not easy. It's very hard, actually. And we know other techniques. But for example, one thing we had issues is we don't have enough flash on our chip, SAM and 11. So we cannot implement all the security mechanisms in our system. So that's one design pitfall by us, and we should have chosen a larger chip with enough maybe RAM and enough flash. So that's what I mean by the design problem.
Okay, thank you very much.
Thank you.
Okay, thank you.